This paper presents an occlusion-free immersive lens technique for spatiotemporal visualization in 3D urban analytics. There has been an increasing availability of time-varying data on 3D urban buildings. However, 3D urban visualizations must still deal with at least two ongoing challenges. First is the problem of visualizing four-dimensional data on buildings. Users must typically switch between different views and different time steps when exploring spatiotemporal data. The second problem is of self-occlusion, wherein a single building occludes itself from some viewpoint. In this work, we propose a new immersive lens visualization to address these ongoing challenges by integrating a cutaway de-occlusion technique and a temporal plot that conforms to the building footprint. To deal with the problem of exploring four-dimensional data, visualization taxonomies classify visualizations into four spatial temporal designs: linked view, embedded view, spatial juxtaposition, and temporal juxtaposition. In this work, we utilize an embedded design. This design affords co-locating spatial and temporal data within the same view and co-visualizing multiple temporal instances simultaneously. To deal with the problem of occlusion, another taxonomy classifies visualizations into 5 de-occlusion designs. In our work, we employ an X-ray design which provides static de-occlusion, in which the target is made fully visible from a given viewpoint, and at the same time, the surrounding spatial context is adequately preserved. To visualize spatiotemporal urban data within our immersive lens using X-ray de-occlusion, we use a conformal mapping algorithm to plot temporal data in a manner that conforms to the building footprint. The image here shows the steps of the algorithm. After extracting and topologically partitioning the footprint, the algorithm segments the footprint into smaller subpolygons. It then computes a conformal map for each subpolygon. Each conformal map consists of two main components: level sets representing distances from the footprint boundary, and sector curves that segment the different building facades. For a building footprint like the one shown in this example, the conformal mapping algorithm generates a geometric layout consisting of multiple nested bands. This example has 3 bands. The bands are not only nested, but also conformal as they approximate the shape of the building footprint. We design our temporal plot on top of this nested conformal layout. To convey temporal ordering, we use a polar radial axis with time progressing outwards. In this example, there are 3 nested bands, each representing one time step. The innermost band represents the earliest time step, and the outermost band represents the latest. To encode temporal attribute, we use a color-based encoding as it is a common way to encode 3D urban data and does not suffer from perspective distortion. Lastly, to address self-occlusion and get a clear view of the temporal plot overlaid on the building, we employ a view-dependent cutaway which preserves the overall layout and context of the building. We apply distinct rendering styles to the front and back faces of the building surfaces to enhance the perception of the cut and reinforce the overall shape of the building. When it comes to interacting with our lens, we differentiate between global and local interaction spaces. In the global space, we use a virtual table metaphor where small lens duplicates are placed on top of a virtual table that always remains at arm's length. Tapping a lens duplicate activates its local interaction space where spatiotemporal exploration tasks can be performed. We support radial gestures moving inward or outward from the lens center to interact with the temporal dimension. For example, users can navigate across time intervals using a radial drag gesture. We also support angular gestures around the lens center to interact with the spatial dimension. For instance, to filter according to specific spatial directions. User controls are also provided to filter according to specific temporal attribute values. To evaluate our proposed lens visualization, we conducted a user study with a between subjects design with 28 participants, a realistic urban model, and sunlight access with added synthetic noise as the temporal attribute with 4 time steps. We evaluated 3 visualization designs. First is temporal juxtaposition. In this baseline condition, the user can only see 1 time step at a time. The user also has to physically navigate to see data across the building. Second is temporal juxtaposition plus X-ray. In this design, the user can only see 1 time step at a time, but the X-ray design reveals the data across all sides of the building. Third is embedded plus X-ray. This is our proposed design, in which the user can see all time steps at once and across all sides of the building. While using these visualizations, participants performed 6 tasks that required them to search across all sides of the building to find the time range during which the attribute value has its longest continuous growth. Throughout the tasks, we collected and analyzed both quantitative and qualitative data, such as completion time, error, head position and orientation, and questionnaire responses. From the gathered data, we examined pairwise mean differences and obtained density maps showing participants' positions. We summarize 2 key takeaways here. We observed that X-ray capability alone significantly reduced the need for navigation, which in turn led to a significant decrease in completion time in the 2 X-ray enabled visualizations. On the other hand, we found that co-visualizing time across space did not significantly affect completion time. However, it had a positive effect on both task accuracy and user confidence. For a more detailed discussion of the takeaways, please consult our paper. To conclude this presentation, we reiterate our main contributions and highlight possible future directions. Our work tackles 2 ongoing challenges in urban visualization: visualizing 4-dimensional spatiotemporal data and dealing with self-occlusions. To tackle these challenges, in this paper, we proposed an immersive lens visualization that integrates a view-dependent cutaway deocclusion technique and a temporal display derived from a conformal mapping algorithm. Our evaluation results confirm that our proposed embedded visualization with X-ray deocclusion benefits task efficiency, physical effort, and user confidence. Possibilities of future research include investigating other spatial encodings such as glyphs, or bridging spatial and thematic mappings to see if spatially embedded abstract encodings can properly support spatiotemporal analysis in 3-dimensional urban buildings.